Hello, everyone. My name is Claire Kopenhofer. I'm going to be a fifth-year graduate student at Michigan State University in the Departments of Physics and Astronomy and Computational Math, Science, and Engineering. I'm here today to tell you about my work I've been doing over the past 4 years, and I'm giving this talk titled Gas in Motion, on how simulated galaxies control their star formation. So usually when you think of a galaxy, you might think of one of those really pretty Hubble images that shows a bunch of stars and maybe some gas and dust, usually in a spiral, but sometimes also in what we call elliptical. But there's actually a lot more to the galaxy than just that. Galaxies live at the center of what we call dark matter halos. This is a blob of dark matter that holds the whole system together with its gravity. And recently we've come to appreciate that there's a lot of gas outside of the galaxy as well, that is kind of difficult to see because it's kind of low density. But we call this the circumgalactic medium. And it's actually quite a substantial part of the system. It accounts for up to half of the baryonic matter in the system, that is non-dark matter. So it's about comparable to the galaxy in the very center. And it's also what we call multi-phase. That is, it's a mixture of hot diffuse gas and also cooler, cold clumps of gas together living in the same medium. The circumgalactic medium is a very busy place. Sort of our current understanding of it is you have a lot of different gas flows passing through it at any given time, whether that's accreting gas from outside of the galaxy or gas recycling from outflows in the galaxy itself. And it's a very, very busy place that kind of mediates all these different gas heating interactions that go on for the galaxy. So what we have for a situation is we have this multi-phase circumgalactic medium acting both as a gas reservoir and as a gas mediator. We also know that gas has to be accreted throughout a galaxy's lifetime if it wants to sustain its star formation. It doesn't have quite enough in the disk itself to keep forming stars for very long. And finally, we know that galaxies must tune their stellar mass to match sort of what's expected from the dark matter mass. There's a really tight relation between the two, between dark matter halo mass and stellar mass. And so this gives us a picture where gas must be added to the galaxy in some sort of controlled way. We call this self-regulation. And the circumgalactic medium is likely a very good candidate in the self-regulation mechanism. Now, one way the self-regulation could occur has been laid out by a theory known as precipitation. And in this theory, you have gas that over time cools in the circumgalactic medium. The gas is always cooling, but at different rates depending on its temperature and its composition. Now, some of this gas will go on to accrete onto the galaxy and lead to further star formation. More stars forming means more stars dying, which leads to supernova-driven outflows. So supernova, when they explode, especially when there's many of them near each other at the same time or in a small amount of time, are capable of driving very strong winds out of the galaxy. This blows material back into the CGM, but also increases its temperature and kind of pushes the rest of the gas out of the way, lowering the density. This ends up lengthening the amount of time it takes for the gas to cool. And so this, for a while, will shut off cold gas accretion, but eventually gas will cool back down again, and the cycle will start back over. And this is sort of a picture that we have in our minds of a mechanism that could plausibly regulate the star formation in the galaxy. Now, previously, there have been a lot of idealized simulations of galaxies. Now, when I say idealized, I mean very sort of simple and efficient. It's nice to look at isolated galaxies sitting alone by themselves in a box, basically, because there's a lot of complicated factors in the universe that affect galaxy evolution. If you want to understand sort of how galaxies act on their own, you can use what we call isolated galaxy simulations or idealized simulations. Now, historically, there have been a lot of simulations that have focused on having a star-forming disk, but no circumgalactic medium. These include the Agora simulations also some from NASA 2016. And it's not that people left out the CGM on purpose, it's just that there wasn't really a lot of widespread recognition of how important it could be at the time. So recently there's been a lot of simulations also focusing then on the CGM. But the thing about these, like in Fielding et al. 2017 and Lee and Thomas in 2020, is they don't explicitly include the disk. They have sort of the effects of stellar feedback. They have winds being driven out from the center of the simulation, but they aren't tying star formation directly to the circumgalactic medium. So my work that I've been working on has combined both the best and the worst of both of these worlds by bringing together the idealized disk and an idealized circumgalactic medium together in the same simulation. I have called these the Sisyphus suite. Our target questions with these simulations are, first and foremost, can we make a self-regulating system? And if we do make a self-regulating system, does it do so following the precipitation model that has worked really well for higher mass galaxies than what we're studying with this suite? And finally, how robust is self-regulation to variations in the initial conditions? We expect it to be sort of an equilibrium kind of state, a dynamic equilibrium, and we want to know, is it an attractive equilibrium? How far can you stray from sort of the conditions of precipitation before you end up not self-regulating? So to do this, we use a Milky Way-like idealized isolated galaxy. That means we're targeting a disk galaxy about the size of our own. You can see sort of what the disk looks like in its initial conditions in the lower left corner, or in the lower right corner, excuse me. The left side is viewing the disk face on, and on the right we have a zoomed out view of the edge of the disk. So it's just kind of a thin slab of gas sitting at the center of the domain. We have gravitational potentials included, and we allow star particles to form to represent populations of stars. We don't quite have the resolution for individual stars. There's rotation in the disk, which is necessary for it to be a disk. But we also have rotation in the CGM, which is not something that I've seen explicitly added to this kind of simulation before. And finally, the circumgalactic medium has been set up with the density and temperature profile that we would expect from a precipitation-regulated system. Now, there's a couple of variants that we do of these simulations. First, we have one that works as a control where we disable stellar feedback, because we want to sort of illustrate that feedback is a very necessary component of these systems and how they regulate themselves. We also have one where we vary this initial ratio called the ratio of cooling time to freefall time. We start at a value of 10 and we drop it to 5, and we also raise it to 20. This is an important quantity for precipitation. And finally, we have variants where we look at different rotation profiles in the CGM, including removing rotation. For the purposes of this talk, I'll be focusing on that control where we disable stellar feedback, star forming, and also the variants where we tweak the initial cooling to freefall time ratio. Now, I mentioned before that I'm sort of having the best and the both worlds, worst of both worlds, with these two different kinds of simulations that we've had. And that's because the disk in these idealized simulations can be a little bit tricky to live with. So you want to have a pretty simple setup. And so what you do is you have basically a cold, little wedge of disk sitting at the center of the simulation. It's supported radially against collapse because of its rotation, but there's nothing that supports it vertically. And so as soon as the simulation starts, the disk starts to compress and kind of smush out the sides. This drives up the density very high and causes a lot of rapid early onset star formation. This very early star formation then causes a lot of feedback. So this is a zoomed out version of the previous picture showing basically bubbles upon bubbles blowing away the circumgalactic medium that we very carefully set up. And this becomes a problem because the circumgalactic medium, gas in it that's going to cool and accrete onto the galaxy, needs time to do so. But the stars form much faster than the CGM can sort of start to interact with the galaxy. And so what happens is you've disrupted the system so much that nothing's going to happen unless you run your simulation maybe for billions upon billions and billions of years, maybe even longer. And that's just not feasible for answering our question. So what we decided to do was we decided to ramp the efficiency of stellar feedback in these simulations. So for the first 1 gigayear, we allow stars to form at a very low efficiency so that we can sort of burn away those artificialities of the initial conditions, have star particles there, but we don't blow up the CGM and ruin the very careful initial conditions that we have. So, and then after 1 gigayear, we start to ramp up the efficiency to something that produces more physically reasonable values. So this is the same sort of image on the right here. It's the same scale, pretty much the same time, but with the feedback ramp in place, you can see that no longer has our circumgalactic medium been destroyed by aggressive feedback. So let's get into some simulation results. First, this wouldn't be a simulation talk if I did not have a medium. I'm going to go ahead and get that started. started, let it play on loop. So what you're seeing here is on the left, we have a view of the galaxy disk from the face on, and on the right, we have a view of it from the edge, much zoomed out so that you can see the bubbles of feedback flowing into the CGM. On the top, we have the density, and on the bottom, we have the temperature. So what you see is for the first gigayear where feedback is really inefficient, you see the disk collapsing and sort of swishing out radially. But then, after stars have been allowed to form initially, and the star formation rate drops, we ramp up that feedback, and you start to see big plumes of outflows going into the circumgalactic medium. And you also see cold gas continuing to feed into the galactic disk from along the sides. And so this is a look at sort of our fiducial simulation, and we will then get into comparisons with it here in just a moment. I'll let this finish up. All right. So now to start quantifying some things a little bit more, let's get into what we expect out of our simulations. First of all, there's that question of, are these self-regulating? Now, how do we interpret self-regulating? We're looking for a roughly constant stellar mass over time. This gets back to that idea that the stellar mass is pretty well tied to the dark matter mass of the galaxy. We expect to see gas infall, allowing stars to form from more than just like the gas that was already in the disk. Because if there isn't infalling gas, it's not really self-regulating. It's just using all the gas that was already there, and we'll eventually run out of it. We're also hoping to see long-term stability of the CGM structure, especially in its entropy profile, which is a quantity very important to precipitation theory that I won't be going into too much. We're also hoping to see that this is an attractive equilibrium state. So we have all of those variations in the initial conditions, and we want to see if they also end up self-regulating. And finally, we want to look for the hallmarks of precipitation, which shows up in that cooling to freefall time ratio I mentioned when I had variations. So getting into the self-regulation, we'll first look at the mass growth. This plot shows the mass over time in the disk in the solid line, the stellar mass in the dashed line, and the gas mass in the disk in the dotted line. And on the left, we're comparing the fiducial in blue to our control variation with no stellar. And you can see there that the stellar mass for the control starts to grow over time and just keeps growing while the fiducial levels off. And so this sort of looks like self-regulation from that stellar feedback. On the right, we show the fiducial model compared to the variance with the initial, different initial to cooling to freefall times. And you see, very important here, that all three of these end up at pretty much a constant stellar mass. Those are different stellar masses. They do not come to the same mass, but they all sort of stop growing over time. You can also start to see in that first 1 gigayear the differences in the circumgalactic medium and how it feeds gas into the disk because of how they grow their stellar mass and deplete their gas mass at different rates. There's differences in the variations, even though they appear to all come to a self-regulating state. Next, we look at gas accretion. Here we have the gas flux radially into the disk. Negative values are infalling gas. And on the left, we're looking at the cold gas. This is less than 10 to the 4 Kelvin, which, maybe not as very cold in real life, but is cold for CGM research. And on the right side, we have warm gas, which is between 10 to the 4 and 10 to the 6 Kelvin. And this gas is very important because while it's not what we consider cold, it's able to cool very efficiently, and so will become cold relatively quickly. Notice that the two plots have different scales, but we do definitely see cold gas inflowing, especially at those early times before feedback can push against the CGM and sort of cut off some of that infall. Now, these initial wiggles in the cold gas towards positive values, again, this is radially out from the disk. So this is from the initial compression of the disk and having it smoosh out the sides. It's a bit of a numerical artifact from our setup. And then we also have, in the warm gas, you can really see a big difference between the cooling to freefall time variance. It doesn't show up so much in the cold gas comparison in the warm gas. It's very interesting. And then finally, in between the two gray bands, I forgot to mention those, but maybe you figured that out from what I talked about earlier. This is the span of time where the ramp in the feedback efficiency is active. you can start to see the impact of feedback lessening that influx of warm gas. So there's a lot of expectations and a lot of analysis going on in this paper. It's all kind of work in progress. But what I can tell you from sort of what I presented and work that I've done in the background is that we do meet all of the hallmarks of self-regulating that we really have. Constant mass and long-term stability of the CGM structure. However, it's kind of ambiguous. It's very much like pen-depend case on whether or not it's an attractive equilibrium or if it's precipitating regulating. Some of the variants are, and some of the variants look more like they are just heated so much that gas can't infall, and that's why they stop star forming rather than being self-regulated. And I'm happy to talk about that more in the questions. So to summarize, we set out with the goal of making a model galaxy that self-regulates its star formation through precipitation in the circumgalactic medium. We did this using simulations of isolated, idealized galaxies that directly model both the circumgalactic medium and the dense star-forming disk. This is not something that we've seen done before. And it turns out it's because the idealized nature creates a lot of challenges, because your cold star-forming disk will do exactly that. It will form a lot of stars in its initial moments of the simulation and can undo your carefully chosen CGM initial conditions if you don't do something like we did, where you ramp the feedback efficiency. I presented just a few of our simulation variants, and the ones that I showed do all achieve a steady lifetime stellar mass, which is one of our hallmarks of self-regulation. However, only a few of those are regulated via precipitation. Others appear to shut off star formation just by excessively heating the gas, and so there's an interesting difference in the initial conditions and what effect that has on the system. So I would like to thank the CSGF for funding my research for the past 4 years. I would not have been able to work on this long but very rewarding project without their assistance. And I'd also like to thank them for letting me attend a summer school and miss one of the annual review programs 1 year. That summer school was sort of a one-off and was very foundational for me meeting a lot of members of my community. I very much appreciate the support of the CSGF, both financially and also in terms of just personal support. Thank you very much.